standard tools of semiconductor manufacturing are good enough, or say almost good enough, to make exactly what we say we will do. Right now, we make 2 NV centers in a defined distance, and that's, so to say, the major breakthrough also, that we can do that reproducibly. People have found pairs, like 2 NV centers that are coupled. A couple of years ago, PhD students had to look for a long time because it's very rare that by chance in a natural diamond, 2 NV centers are so close together that they couple and can exchange the quantum information. But we can exactly do 2 of them as of now, or as of a couple of months ago. We can do that reproducibly. So we can create those pairs, which is the first and most important step to scale. And then you add a third one and a fourth one. And of course, every next step has its challenges and so on. But that is exactly the point. It is doable. And yeah, the little pitfalls are like, what is the exact precision that you can do it with? And yes, we need nanometer precision. But if we look at the current, say, MOSFET transistor technology, okay, good, it's called 2 nanometer technology or 2 nanometer node, which is not really truly 2 nanometers. But nanometer range is absolutely in the grip of current semiconductor technology. So it is doable, and it has a great advantage that the methods are there from the toolbox of semiconductor physics, nanotechnology, and so on.
Welcome to another episode of the Quantum Economy Podcast. Today I'm joined by Professor Marius Grundmann, co-founder and co-CEO of SaxonQ. With an H-index of 95, according to Google, he is on par with Nobel Prize winners and a true textbook authority in semiconductor physics. Now with his team, he is pioneering NV, nitrogen-vacancy centers in diamond, and building a mobile, room temperature scalable quantum computer that can challenge the cryogenic approaches of IBM, Quantinuum, and others. This is truly an exciting episode, and you should listen in. This is my conversation and the Quantum Economy Podcast with Marius Grundmann. So I've been looking forward to this because a couple of years ago I ran across the NV Center technological approach to quantum computing and the whole aspect of diamonds, and I was fascinating. But then I ran into all these challenges on they're not scalable, quantum communication, quantum sensing. This is not a true quantum computing hardware technology. So it left me, and then all of a sudden I run into SaxonQ from Leipzig, standing on the shoulder of giants, of some of the greatest thinkers of all time. And there's a guy, Marius, that has a close to 100 H-index, who has worked on semiconducting, saying that we're going to build a room temperature quantum computing built on NV centers. And I was like, whoa, this I have to look into. So I've been really much looking forward to getting you on the podcast, Marius, and I'm thankful that you take the time. So first of all, can you just explain to me what is NV centers, and why do you think this is a relevant approach to building quantum computing?
Anders, hi. Yeah, pleasure to do so. The NV center, first of all, it's called a color center. It's a defect in the crystal lattice of diamond. So the N stands for nitrogen and the V stands for vacancy. So instead of 2 carbon atoms, we have a nitrogen atom and a missing carbon atom. That's just, let's say the atomic configuration of that center. And in detail, you need a negatively charged center. So we talk about NV minus centers that can do this quantum computing because we use the spin of the electron. So that's our first qubit. And yeah, this has been done since 25 years, roughly. And in the first papers, it was said, yeah, this can be great for quantum computing. But nobody really has built a quantum computer except SaxonQ or so, because it's not so easy to create those centers in an industrial fashion. You find those centers in a natural diamond, say in a yellow diamond or in red diamonds or so, but we can really create these centers in a reproducible way. And that opens the way to use this qubit in a, say, orderly fashion in a quantum computer. And we have built the first quantum computer, and it works at room temperature because the center has its, say, spin properties. The qubit is like a spin qubit, has these spin properties at room temperature. However, if we look at the detail, when we do the calculation, the spin qubit is actually extremely cold because, you know, the quantum algorithm always starts with the initialization. I mean, every computer, even a classical computer, starts with bits in a certain order, say all 0 or something like that. The quantum computer needs to do that too, and that relates for a spin qubit to an extremely cold temperature, which we generate in the hot diamond, in the room temperature diamond, and that is with a green laser pulse. It's called optical polarization. The qubit takes on one of the spin orientations, so you start with a defined qubit value, say 0 or 1, that depends on your definition. Yeah, and then you can manipulate that electron with microwaves, so it's called electron paramagnetic resonance, and the electron is connected to surrounding, or it interacts with surrounding nuclear spin qubits. So we look at the spins of nuclei in the vicinity. Those are carbon atoms with the isotope 13, so they have a nuclear spin. And that interaction then allows us through nuclear magnetic resonance, which we know, say, from the MRI scan, the doctor, we can also manipulate those nuclei. So when you think about the doctor scanning your brain or something like that, you look at the hydrogen atoms, the water in your body, but we look at the nitrogen atoms and the carbon atoms with that nuclear resonance. So just in a nutshell, we can manipulate those spin qubits in the NV center. And the challenge now is to go beyond, say, 1, 2, 3, 4 or so qubits, but to really make many of them, because the first step, which is useful, is to go beyond, say, 40 qubits, which is still, we can still simulate 40 or a little bit more qubits with a classical computer. You need a lot of memory, maybe, like 2 to the 40 states or something like that. But to go beyond that, you have a machine that you cannot really simulate anymore. And then we all know that like useful problems maybe need more than 100 qubits or something like that, at least, if not more.
Yeah.
So the challenge of the NV technology is, in my view, mostly to make more than one NV center and bring those NV centers, say, in a row or a square array, and then you have a scalable technology. It's, say, in a simplified way, it's like an ion trap where the ions are already trapped. They're like fixed in the diamond lattice.
So you have all ions permanently trapped, basically. So if you look at the approaches of like PSI quantum or IonQ, you would now have a perfectly permanently trapped ion.
Yeah, it's very unlikely that in a diamond the atoms will change their place. So they're fixed in this lattice, and they're also atomically precisely located. Say it's clear that everybody has like its space in the lattice, so to say, yeah.
But diamonds are different, though. They aren't similar. So there are there challenges in the various structures of the diamonds? And maybe also to add to that question, I've been thinking about this. You know, what is so we talk about the 4 qubits and you build the computer, but if you look at the approaches like of other players, what are the differentiator where you are so positive that you can also scale it? Because my understanding is that diamonds aren't similar, so there are different, approaches to using the technology then, or am I wrong about that?
Well, I would say that the qubits that we use are in the range of the distance of NV centers in order to make a useful coupling, so you can move the quantum information from one NV center to the next, is in a range of, say, 5 to 15, say, let's just say 10 nanometers. So they interact with each other. And on that scale, a reasonable diamond is really perfect. I mean, the defects in a diamond can be other point defects, it can be dislocations, grain boundaries, or whatsoever. But those are like more on a macroscopic scale, because even if we have 1,000 qubits, we need less than a square micrometer or square cubic meter of material. And it's in the current technology, we buy our diamond chips. They're not perfect, yes, absolutely, but there are perfect patches that are much larger than what we need. And so on that very small space, the diamond is really perfect and every atom is where it is supposed to be. However, it's very important that by our fabrication procedure, we do not add defects that we do not want. So our technology is to implant the nitrogen. So we start with a perfect diamond and we implant the nitrogen. So we shoot it in, not very deep. And in that process, it's possible that you create lattice damage. That's why we have developed a procedure, including annealing steps, that gets rid of that initial damage. But this happens at like, say, 1,000 centigrade or something like that. And then when you cool it, the diamond will not move any atoms anymore. And the key feature that we use is to also implant sulfur with it. So with the sulfur implantation, we do two things. The sulfur helps to create the vacancy next to the nitrogen. So we really have NV centers and not just the nitrogen. And that's extremely important because we only need one nitrogen atom to make an NV center. If you don't use the sulfur, you need about 10 or 13 nitrogen atoms to make one NV center. But then the other 12 are laying around and disturb the entire system. So that must be avoided. And that's our trick, that we really only make into the lattice what we really need.
But do you then move from more error protected qubits, then you have to struggle with error correction? Is that the consequence then?
Well, I guess the consensus is that eventually every qubit system needs to be error corrected. However, there are fault-tolerant algorithms. But the first thing you need is like a good fidelity of your operations, because the better the fidelity, the less error correction you have to do. So the NV centers from the literature actually show among the very highest fidelities of all qubits that are reported. So we have a very good starting point. And then, yes, there are also reports on how to error correct NV centers. In particular, you can use one NV center together with its nuclei as a cluster that, say, error corrects itself in this sense, yeah.
I want to get back to that, but I'm also curious a little bit about you, because I mean, you're obviously a textbook level authority with all the publication and citations that you've had. You've done a bunch of work with semiconductors, and as I mentioned at the beginning, stemming out of Werner Heisenberg's Leipzig and all the things that you've been working on. What was like the point that made you step out of academia and become an entrepreneur, a business person, and a visionary to build because you talked a lot about that in the beginning, also about the industry application and the business implications. So what was the drive for you to set up the company?
Well, let's go back many years, like, oh my God, like 40 years or something like that. When I studied physics, and I went into the applied physics group at the Technical University of Berlin. And after now it's master, but back then it was a diploma, I thought, well, do I go to industry or do I go to academia? So I said, okay, let's do a postdoc first, and I can still decide. And then after that, I decided to go to academia because I just love the research. But I always thought, well, the eventual purpose, at least of semiconductor physics, is to really make devices and do something, good for humanity, or to at least drive technological progress. And then I worked on two issues, or two topics, mainly in my career. In the 90s, I worked on quantum dots. Quantum dots that are now used, say, in like color TVs or optical amplifiers or something like that. And those quantum dots we made as small nanocrystals. And I stopped that research because these nanocrystals they were similar, but they were not identical. They had a little bit different size, a little bit different shape, and still to that day, it's not possible to make these nanocrystals exactly identical. And then I moved to Leipzig in the year 2000, and I switched topics because, good, it was a new position, I can maybe do something else with my life. And I went into the field of wide gap semiconductors, transparent semiconductors, like gallium nitride, gallium oxide, zinc oxide, and also diamond, which is a matrix that can host quantum wells, nanostructures, and so on. And now the NV centers are these quantum dots in a wide gap matrix. So that means I combined everything, and then it turned out that it can be industrialized. At least we have started that path. We're not done yet, but we started that, and we said, okay, together with my colleague, Jan Meyer, who does the implantation especially, we said, now it's a way to do something really on the industrial scale, not just stay in academia and keep writing papers. Now, as you mentioned, I have over 700 academic peer-reviewed papers, and whether I add 10 or 50 or 100 to them, yeah. I mean, for me, that's not a real challenge, but there was also a challenge to really bring one of these fruits of the research really to full fruition into a real application.
Yeah. No, I mean, that's very fascinating. Who were like inspirational sources or people that inspired you when you go back? I mean, talking about this time, there were some early visions of quantum computing. We had pioneers in the field that had a theoretical, at least like a vision of a quantum computer, but there were no actual practical application of such. So were there people that inspired you?
Well, I like Feynman because these books are really interesting, you know. And Feynman made in this dinner speech, there is a lot of space at the bottom. He kind of initiated the field of nanostructures to think about how small can we make structures. Initially, it was thought, how small can we make little motors or something like that, which is now people make molecular motors and do this kind of stuff. And so these quantum dots I did in the 90s were really motivated by, like, I don't know, 30 years ago, Feynman made these ideas. We can fit the entire knowledge of the world, a whole library on the top of a pin or something like that, you know, because atoms are so small. And there's no reason that we cannot move atoms one by one. So in that realm, I came to the field of nanotechnology, and these NV centers are the perfect type of nanotechnology. And that's also one reason why this technology is a great technology, because the NV center is atomically defined. If you think about a superconducting qubit, it's more or less a crossing of like two wires. And if you look at these electron microscopy images, the wires are jagged, the edges are not well defined. It is a macroscopic system that undergoes macroscopic changes, and that's why they need to be recalibrated, and the properties change over time, while in the NV technology, the qubit is atomically precise and defined. So they're not like these nanocrystals that are all a little bit different, but the NV centers are really quite identical.
But do you think then IBM and Google, following the superconducting qubit approach, that they're gonna reach some limitations or have challenges? Is that your assumption?
Well, let's just say every technology has challenges and reaches
Yeah.
eventually some limitations. And it's really hard to know where these limitations are, but it's a fundamental limitation when you have macroscopically large systems that their behavior is not extremely well defined. However, if you have a larger system, it's easier to connect it to wires or something like that. However, we have 8 or 16 qubits and we only need one wire. If you have superconducting qubits, you need maybe 100 wires. So that's a long conversation we can have about the pros and cons of all these technologies. The main drawback, of course, from the practical point for superconductors and also optical computers that need superconducting photodetectors is they need low temperatures to operate. So there's a large periphery overhead to even operate the system, while our system operates at room temperature because we cool the qubits, but we don't cool the crystal or the wires or any other part of this contraption.
Yeah, but I think also then your, semiconductor experience and your publications plays an important role to come to that conclusions, right? So, I mean, is that something that you think you're more promising in the long term? So as we say, the diamonds are the qubit's best friend, and everyone else will have a challenge. So, is that your vision to say that even now you're looking at because my feedback was, and having looked at some of the companies that have tried to build an NV center approach was, well, it's cute, it's nice, but it's more for communication and sensing, and it's not for compute. So when I listen to you, and this is also why I was so interested in getting you on the podcast. You are very optimistic about scaling. You're looking at 80 qubits in fairly near future, and you think you can go way beyond that because of that connectivity. So maybe you can elaborate a little bit why you think that you will be able to scale also against these competitors who obviously have deep pockets, right?
Yeah, we have operated what we do with rather little startup funding, we have to say. And yeah, of course, we need more money to do what we want to do. But the point is that the standard tools of semiconductor manufacturing are good enough, or say almost good enough, to make exactly what we say we will do. Right now, we make 2 NV centers in a defined distance. And that's, so to say, the major breakthrough also, that we can do that reproducibly. People have found pairs, like 2 NV centers that are coupled. A couple of years ago, PhD students had to look for a long time because it's very rare that by chance in a natural diamond, 2 NV centers are so close together that they couple and can exchange the quantum information. But we can exactly do 2 of them as of now, or as of a couple of months ago. We can do that reproducibly. So we can create those pairs, which is the first and most important step to scale. And then you add a third one and a fourth one. And of course, every next step has its challenges and so on. But that is exactly the point, that it is doable. And yeah, the little pitfalls are like, what is the exact precision that you can do it with? And yes, we need nanometer precision. But if we look at the current, say, MOSFET transistor technology, okay, good, it's called 2 nanometer technology or 2 nanometer node, which is not really truly 2 nanometers, but nanometer range is absolutely in the grip of current semiconductor technology. So it is doable, and it has a great advantage that the methods are there from the other toolbox of semiconductor physics, nanotechnology, and so on.
I want to get to that, software implication layer. But first, I just wanted to come back to that funding part because you said you're operating out of a fairly small budget in comparison to some of the competitors. First of all, why do you think that is? And secondly, as we are seeing a quantum race path towards quantum supremacy, we are seeing huge funding rounds. What role would public funding or governmental programs for you also coming out of Germany play here? And why should these programs now start to look at SaxonQ? I mean, we know Alice and Bob, IQM. We talk about a lot of these European players that are turning into unicorns. What are the core things that governmental institutions need to understand in order to say we have to put our money into SaxonQ as well, or in SaxonQ?
Yeah, we have done everything with 1 million euros in the seed round, or maybe it's for deep tech only a pre-seed round if you want. And we have earned the rest of the money by delivering quantum computers to public players, German Aerospace and the Fraunhofer Gesellschaft. So they use these computers, they test them, and that has helped. I mean, DLR got the money from the federal government of Germany. So it is, in this sense, publicly funded, but it's not through a project, but it's really through delivery of actual quantum computers and actual working machines, which for us is important. We also have cooperation with the university, with funded projects, but projects, it's not the point of this company. The point of this company is to deliver actual machines with each step of development, better machines with more qubits, better qubits, a simpler setup, and a smaller footprint, and so on. But yeah, now we're in a funding round. We look for much more money because we need to accelerate our development with more people, with more equipment, to really deliver of what we foresee in the development pipeline.
Talk a little bit about that roadmap. So you mentioned the 4 qubits, you mentioned like the first connectivity that you have. What is the path forward? If you look into 2026, 2027, 28, what is your pathway for scaling?
Well, there are 3 ways to scale. I think most essential is scaling the number of qubits, because fidelities are good, and there are 3 ways to increase the number of qubits. The first one is to increase the number of NV centers. We already discussed that. So we go from 1 to 2 to 4 or 8, something like that. The second is to increase the number of nuclei that are connected to a single NV or to each NV. And currently we have 3, but that can be 4 or 5 or 6 or 10 in the literature. 26 or 50 are reported, but there's some sweet spot. Let's maybe say we go to 10. So then we have the number of qubits from the NV, the electrons, which is say 8 NV centers, times 10 nuclei, you have 80 qubits on a volume which is smaller than a micrometer or something like that. And then the third way to do it, because a system is rather simple, small, and also not very expensive, is to have a multi-core computer where we have several of these instances. So you don't have only 1 times 80 qubits, but 4 times 8 times 128 of these that can work either in parallel or use algorithm cutting to separate a problem onto different quantum computers. I mean, people talk about connecting quantum computers through like the internet. There was just a Kerber Prize, which works on, well, the lady, Frau Wehner, she works on some operating system that connects different quantum computers. But how many quantum computers are there? Ours are so small and inexpensive, relatively, that you can build 64 of them or 128 or some other larger number and connect them if you want. So then the total number of qubits will be gigantic very quickly. However,
so you have basically, if you have 80 qubits in the core and you had 128 cores,
yeah, we go to 10,000 qubits quickly. Of course, fully entangled. And when we talk about one core, we talk about fully entangled qubits, of course. When I say the NV centers are all fully entangled. Of course, fully entangled qubits are worth more than like 2 times half the number of qubits. But still, if you have several of these machines, it's still better, and we can make many of them.
That's very interesting. And I mean, what is the timeline for this? When do you think you can have the 10,000 qubit threshold? Or
well, we're currently building a twin machine where we have 2 cores. And once that's done, it of course needs to like some software and some logical things to it, but we have it done by the end of the year. And then there is no limit to go to 4, 8, 10, 2 to the power of 10. So we want to go to, say, 80 qubit cores and then make 100 of them or something like that. Maybe even cores on the same diamond chip, because, yeah, the NV center with 80 qubits is still less than a micrometer. So on a 1 by 1 millimeter chip, there is infinite number of real estate to maybe create many cores even on one chip. Wow. So yeah, then you go quickly to 1,000 or 10,000 total qubits.
Mm-hmm. So how is this compared to the predictions of other technologies? Well, how do you see that hold up in terms of, because I think there is also a very big marketing topic here. People look at, 1 million qubits, that's the threshold, and then you start. So it will change. I predict it will be a different view in 2 or 3 years. But this is for now like the roadmap. You have some benchmarks. How do you hold up in timing compared to these other players in the market?
I think we do very well because, say, on a Hannover Messe, on a Hanover Fair this year, I was at the IQM stand. Let's just give an example. And we had our computer demonstrated live because it's a simple machine. We can bring it there to the stand. People can try it out. Of course, the IQM or IBM system cannot be demonstrated live because there's a large periphery overhead for the helium and so on. But at least at this time, which was spring this time, they say, yeah, we have the 80 qubit chip. But I ask, how many qubits can you entangle? Oh, it's the same as the previous chip, which had 20 qubits. So they entangled 20 qubits. We'll entangle 20 qubits next year. Mm-hmm. We started a little later in this race, but some people maybe have 100 entangled qubits, that's fine. But going to 1,000 is a huge step, and nobody has demonstrated that even closely. So I think we'll be very soon on par with like any other technology on the market in terms of fully entangled number of qubits. And then you go to the details, like what are the fidelities and right. How quickly can you read in information in and out and so on. I mean, but we'll be there very soon.
Wow. So what are the limitations? Is it people? Is it capital, processing power? What are like the core challenges for you now ahead?
For the company, it is equipment. We currently rent equipment at the university or so for some of the important steps. And people, yeah. Mm. We have 10 engineers that do that. Other companies have like 100. And so that makes a difference. We just need to accelerate.
Yeah. Will you have 10x progress if you have 100 engineers? Is it that simple, or is it do you just need more? Because that's interesting. It's uplifting to say that.
Absolutely. Well, we want to build it up. Of course, not employing 90 engineers like next month. It will be built up. There's a plan, but. Yeah, you can parallelize many challenges like the chip fabrication, the periphery, the software, and we can use for what we want to do many more people that work together on this subject that would accelerate our progress in the technical development. Apart from that, there's also like administrative positions and organizational things, sourcing, and so on. But the main thing is really the technological progress that will drive the success of a company. Mm. And yeah, of course, there are technological challenges. In this business, if somebody says they don't have tech challenge or even tech debt, it's everybody works on that. And yeah, to be careful. A lot of people say stuff that's actually not true.
Mm. Yeah, I've had already very many different views on the quantum technology space on the podcast, and I'm very curious about like the development, and I'm very interested in seeing new approaches. And what I've looked at is that a lot of the business relevance when it comes to the industry is also to have practical applications. So we talked about that a while ago, circling back to, what are use cases, what are potential revenue streams. And here, I would just be curious to see, like, how do you tackle middleware, software, front end, that application layer? When you is that something that you're going to outsource, partner with, or you want to build something yourself?
Well, we have an automated software that brings any quantum algorithm code, like written in Qiskit or Cirq or something like that, or OpenQASM, onto the chip. So we can execute any quantum algorithm on this computer. Of course, limited to the number of qubits for which that code is written. So the system automatically, finds the one atom that we work with, or the few atoms, and does a calibration, of course, but many parts, once calibrated, do not need to be recalibrated because it's an atomically defined and precise system. And then, yeah, it's code to chip, that our software does that. And we have APIs where you can send tasks to our task queue, and then you get the result back. So that is, say what we don't do is the algorithm development really maybe like Kipu or so, because that's just not at this point our main technological focus. But once the algorithms are out there, we can execute them. And of course, it'd be interesting once we have more qubits, then to optimize code. So that's a challenge we'll see in the future. Optimize code for our topology, which is like a star topology. Each NV has these nuclei, the next one as well. So it's a factor of two more interconnected than, say, the IBM topography. So we can benefit from that. And there are native gates that may be a little bit different from what you know from superconducting qubits or so. So to optimize quantum algorithms using our native gates is maybe then a transpiler challenge or something like that.
That's also very fascinating. But how can we think about this in terms of real business impact? So if you look at, we've talked a lot about the technological aspect, physical part of it. What do you see as promising business use cases where you can deliver an ROI to an investor, where you could look at actual problems? What I really liked was your take on improving the state of humanity, or the quality of human life. What are use cases that you foresee will be cases where we'll say, now we have quantum computing, this is actually solving or helping solve some really, really big challenges in the economy, in society in general? What are your predictions on that?
That's a very good question, and it's a hard question because I think everybody thinks about how can I make money with this in the end? Where can I make an impact, where I actually make a positive impact in society in the end, or help solve some problems that are relevant. Let's say the following. I see three levels. One is the quantum benefit, one the advantage, and then the dominance. So dominance is the easy part. It's like factoring big prime numbers and doing this kind of deciphering or something like that. Whether that's beneficial for humanity or not, that's another discussion. But if we do with the quantum computing for difficult problems, if we actually manage to solve the same problem faster, and in particular with less energy or less power, that's already a big advantage. If we save even 10% for large language models, some AI learning or something like that, that's worth billions right now. And then the advantages, if we really solve difficult problems that take a long time, that are doable, but you need it faster because you need the result within an hour or a day or a second or something like that. So I think the field will be built from the ground up. We have slowly increasing number of qubits, better fidelities, beginning of error correction, and so on. And then it phases into some of the applications. And it's really hard to say where the first impact is. We think that in the artificial intelligence field, there are algorithms that are fault tolerant. that are doable with physical qubits that are in the, say, in an optimizing kind of way where the perfect qubit is actually not needed really, where we can make the first impact, but nobody will tell you exactly how many qubits or what you need exactly for what. But quantum convolutional neural networks or calculating attention functions or in the end, like image recognition issues or things like that, they can be done with quantum computers, and codes need to be optimized still. And there's a lot of development in the software that I see as one of the first challenges we can take on. But calculating larger molecules is for us interesting because I've come from material science, so that always has been a dream to crack bigger atomistic problems. And I mean, there are 100+ pages reviews on like algorithms and use cases and these things. And yeah, you need enough qubits to really make an impact. And yeah, it's not 30 years away, but it's maybe also not 30 months away. One has to see.
Yeah. No, because I anticipate future development based on exponential development in technology, and obviously not being a physicist, I can't put the math to it. I have the privilege of working with great people that work in their fields, and they explain to me that this is what we also see. But to me, it seemed inevitable that progress is not our path. And if you look at that, you could say that, as you mentioned, you come from the material sciences. So say that, I always say that the periodic table today has about 118, 119 elements, is it? And most likely, within the next 10, 15, 20 years, it will grow to 130. Do we know which elements? Do we know what that is? No, but that will make a huge difference because we'll have other substances to create a different material design, which will help us with a lot of things. And the same I also apply to energy. So I predict that the marginal cost of energy will plunge towards zero within the next 10, 15 years because of progress. And I don't think this is necessarily only true for quantum computing. I think there is a lot of optimization to be done on foundation models in AI with world models. There's a lot of improvement to be done also on the transistors and the chip design with CPUs and GPUs without going into QPU. But this progress to me seems inevitable. And therefore, I just say that this is the future that I think is most likely. And then it stops, people are not very good at anticipating what that means. So if you see this progress also, and listening to you, I think you do, how do you foresee then the world 10, 15, 20 years down the road? What are, the good parts of it, and what are the challenges that you see?
Well, you're absolutely right. I'm not sure about more elements. They need to be stable, and the heavy elements tend to be unstable. So maybe there's that island of stability that could be interesting.
I triggered a physicist.
We'll see about that. But now we have this, the number crunching really can create a lot of materials in theory, and the theories are getting better and better to do a lot of things on the computer instead of the lab, which is much more expensive and slow. So yes, if we have infinite compute power for a reasonable cost of energy and hardware cost as well, I think any problem can be solved. Yeah, you can say, okay, I want a material with a certain strength, certain color, certain this and that, and that inverse design will throw out some kind of either organic or inorganic material in a certain, say, atomic arrangement, and together with that, say, instructions how to make it in the lab or in industry. Say that's a dream a long time in material science, that you can design, you can come with properties of material, and then somebody tells you what material has these properties. And so we get closer and closer to that. Now, in academia, we have the problem that the exercises that we give the students in order so they learn how to do physics, in my case, but or chemistry or math or whatever, the exercises come, as a PDF. They can be uploaded to ChatGPT, and unless it's quite specific stuff, they get a text file with the answers and submit it and learn nothing. So the risk that I see is with this all-knowing AI is that people rely on it, and the motivation to learn what's behind that is small. Let's say we all use pocket calculators, and in the old days, people could calculate much more in their brain and without really that help. So now it has gone on another level that any question more or less can be answered. If you look in the detail, yeah, ChatGPT is not always right in what they tell me about scientific questions. If I ask ChatGPT what my biggest achievements in science are, the answers are quite interesting stuff I've never done. But those are kinks that will be, they will be kinked out in a few more generations of that. And so if you have this all-knowing, we came from like, I need to go to the library and look up articles and copy them and read them, to I can download them easily over the internet, to I don't even need to read the papers. I just have somebody who read all the papers and can give me the answers. But that will be hard for other generations to motivate to learn. And then all of a sudden we all rely on this AI and nobody understands what's behind it. And if that AI dies due to whatever reason, we're back in the Stone Age because nobody has any clue about how anything works. So that's maybe like a dystopian idea, but I think one still needs to understand how nature works somehow in order to do it. And yeah, human intuition is always important for research. It'll be interesting how these softer skills like intuition and creativity will come with much more compute power. Yeah.
When do you think AI or quantum AI will actually come up with new scientific theory or like disruptive creation, not beyond the data? So it's not, I mean, AI is very creative within the data set, right? So logos and ideas and thoughts and poems, what have you not. But when do you think, so that is coming also circling back to the advancements in the periodic table, when do you think actually that an AI or a quantum AI could create something new, a new scientific theory? Do you think that's foreseeable?
Well, whether it's AI or quantum AI, accelerated AI, we just assume that the power of AI will continue to grow exponentially or maybe double exponentially, because with the quantum AI, it can accelerate even exponential growth. It's hard to predict the future, but it will come. And if you give AI the means to make materials, right now we have automated labs that kind of come up with ideas and create materials, investigate them, optimize them already. It's like a fully automated lab. And as a kid, I used to read Stanislav Lem books, and there are these factories that do nonsense things because somehow their program went crazy or something. And they used to do something useful, and then they just do something irrelevant because they went off path for what they were intended. And we're kind of there that a lot of automation happens in science. And I can look at material science mostly, but in science in general, and that AI is guiding experiments and replaces rather smart people that otherwise would work in the lab, or even technicians, Whether something really fundamentally new will come out, like, say, the Nobel Prize idea that takes fruition in maybe 20 years only, that is really hard to say. Yeah, it's really
Well,
hard to say.
you see a development from, and I've touched upon this many times. I've written quite a bit of the topic of a solved world and the implication of such. But what I've been observing is that the Nobel Prize came out of academia. No, now corporate labs have the money, and the physicists and scientists can work on the same challenges in an environment with a lot of funding. It becomes much more rapid because you don't have to go all through these instances and the structures. And some envision that by having a agnostic software layer to various quantum computers and making it very simple to play with, that a quote unquote average person can come up with some Nobel Prize scientific breakthrough in future. And if you take that as an argument, you could obviously also hold the argument that if that is true, then most likely an AI agent that works on self-improvement and can spin out of the structures of a limited content training and have some interaction with the physical world could actually also, in a fairly foreseeable future, actually have some great, groundbreaking breakthroughs in science that has been hidden from the human brain as of now. And I think that's nearer than we anticipate.
Yeah,
I've been
well, possible. I mean, let's think about what breakthroughs. It's always think about outside your boundary, but what are the breakthroughs that we would like to have? Say superconductivity at room temperature or at elevated temperature. Warmer than room temperature actually would be required, but that'd be a great scientific breakthrough to have. Yeah, electrical transport without losses, for example. And yeah, whether that's possible with like regular materials that are not under extremely high pressure or whatever is an unsolved problem. We don't even understand high temperature superconductors, how they really work. And something like that, okay, that's immediately Nobel Prize material. How can we make something like a silicon chip out of organic material? They're way too slow, electrons are slow. Are there organic materials that are as good as silicon, which are much easier to process and or much cheaper to process? I mean, there are many questions you could answer. Can I make, I mean, now we have graphene, can I make materials tougher than steel, lighter than steel, things like that? Which are cheaper to produce, which need less energy to be produced, which harm the environment less, which don't require mining of metals, and so on. I mean, can I make a computer out of organic material like our brain? How can I make that artificially and enhance the functionality? Because we think rather slow on like a millisecond base. Imagine a brain, something like a brain working with gigahertz. That would be a factor of million or so. I mean, you could do more. And I mean, there are like big things you can think about. Is it possible in general? Can somebody work towards that?
Yeah, we wrote a book recently, The Singularity Paradox, where we propose exactly that to quote unquote hack chemistry and biology and to build biological substrates so that we upgrade the human being as in comparison to building an externalized artificial general intelligence. I think, the trial and error, giving the authorities to a machine with a Deus ex machina, God out of the machine scenario is very risky for our species. So the argument is basically, I said, that we have to start with a mensch, with a human being. The agency, as you have been talking a lot about, the creativity and the activity and to do something, the hands-on to build those relationships. And in a solved world where there is no room for progress, right, we lose that very aspect of what I think what it means to be human, to come up with better explanation, and therefore I think it's maybe the only, I would say, possible kind of sort of utopian path is to take a human being and to leave that agency as a mensch, the conscious experience, and to build on top of that, and to then build artificial intelligence on top of a human being. I don't know if you have any thoughts on such a scenario, and what you see that could be a positive path for that, as in comparison to the AGI technological singularity scenario, which I think is a bit of a risk.
Absolutely. Good point. I mean, I use artificial intelligence as a tool right now uh, to enhance, to accelerate my output, so to say, to quickly get a summary of the existing knowledge on certain fields. And it's not always correct, and sometimes the references are made up, but it helps you, and it will be better in a way, and then go from that. But I think we're far from models that really explain things that have not been found, and there will be a big step. And if that comes, then yeah, we have to deal with it. I don't know. It's everything has risk and benefits, and as long as you don't connect the AI to like the nuclear button, it's probably more or less safe.
So you're optimistic about progress. That's a sense.
Well, as a scientist, you know that every progress has its downfalls. Let's look at LEDs. You know, they save a lot of energy, except now LEDs are everywhere and they don't save energy.
Yeah,
So I don't know.
that's the paradox
You
of at least.
illuminate the whole city at night, and I'm not sure then the savings are so big. So it depends. Everything has its plus and minus, and we need to mitigate the risk and politically also make sure that humans do reasonable things and not unreasonable things to each other.
Right. So yeah, I think this has been amazing, Marius. I thank you so much again for coming on, because I really love to pick your brain on the envy centers, and again, you've made a very appealing arguments for what you're doing. So I'm very happy that I got to know SaxonQ and yourself, and I want to kind of sort of close it out with some, some intuition reflections that is for a scientist as yourself with that track record, more of a philosophical note. How do you think about, like, what is it with a human being that is not something that we can find an explanation to? Do you think there is something beyond a reach for explaining what we are, you and I, a human being, a mensch, that is not a part of a scientific or mathematical definition?
Well, I think a big challenge is this consciousness that we have, that we know that we are and we can self-reflect and this kind of stuff. And it's not like, at least you hope to think of that it's not like a reflex, like a born trait, but it's actually an acquired way that you reflect about yourself and the world, and you know you need to die and these kind of things, that you really know that. And how does that develop from a sufficiently complex brain or so? That is for me quite interesting. How does the brain even store information? We don't know that. And why can we not think in our brain how a four-dimensional body looks like? I mean, as a physicist who has dealt with special relativity, you work in like space-time, so it's four-dimensional space, but it's really hard to really imagine that. You always try to do some 2D X versus time plot, and the other dimensions you forget. But if you think about a four-dimensional cube, how it would interact with our world, this hypercube, you cannot really imagine a four-dimensional thing because you're somehow caught in that three-dimensional world. And how can we break out to visualize ourselves higher dimensions? That's really a puzzling thing that is difficult for our current status of brain power, let's say.
Right. No,
And
I mean,
so there are these like somehow intrinsic, or at least felt limits, or maybe intrinsic limits, I don't know, that we can't do certain things with our brain.
Mhm.
or at least it's extremely hard, and only maybe very few gifted, maybe say abnormal people can do these things.
Right.
Some people can never forget things. They
Mhm.
read a book and they know every single word where it is on every page. I tend to not forget plots that I find important. I can visualize them, yes, but I'm not that. So there's some people have amazing brain traits, which are sometimes like borderline clinical or so. But so the brain can do much more, and it's kind of interesting how. And the human brain has only developed for a couple of, say, 10,000 years with more input. And it'll be interesting how it develops in another 100,000 years if we don't kill each other all
No,
off the earth.
yeah,
And
we figure it out before that with the
yeah,
rapid.
whether there's like a further development within this brain, or maybe there's like another gene modification, or that allows us to learn 100 languages easily, or something like that. Who knows? That is kind of an interesting thought.
Yeah, I'm very interested in that. I'm looking into some a friend of mine is going to having on the podcast. Runs a company that is doing 3D DNA sequencing, and how can you get into look at that, and how can you create life, and what you touched upon, obviously, coming back to Nagel's work on how does it feel like to be a bat, our qualia, the sense of the experience of our own experience. And I mean, philosophy and science alike have had many theories on what that is. You have the integrated information theory of Tononi, you have panpsychism, and all of these various views. And I totally agree with you. And um, I like scientists that are open to that dimension of the inexplicability of consciousness. And I like the word in German, Lebendigkeit, the liveliness of life itself, the vitality. What does it mean like to feel to be alive, right? So I think this is the magic. And I always argue that if we still have a question that could theoretically be asked that has not yet been answered, we are in a good space.
Yeah,
So
but
that's
we have to think: is it really magic, or do we just not understand it? Because
right.
many
Exactly.
things were pronounced magic, and say like thunder and lightning or other stuff, and now we like understand this
Yeah.
to some degree, and at least we think we understand the basic mechanisms. And it's a challenge. Maybe at some day we understand exactly what gene mutation created then really that we are human, and what other gene mutation maybe can make us superhuman in a good sense. And maybe we understand what the consciousness comes from. And sure, the AI research will probably contribute to this answer. And that's, you can't imagine it, but it's often that when we found it out, we're like, yeah, of course it must be like that. Once you see the solution that people have done in the past, you're like, yeah, of course it must be like that. How could people not think like that before? So once you break this knowledge barrier, then somebody explains it to you, you say like, oh yeah,
Yeah.
I guess
No, well,
now we have the solution. But if you look at even like say the atomic theory, a lot of theories were made and only one prevailed, like
right,
Bohr and Heisenberg and so on. And
right.
people had other ideas about it, and then science decided, no, it's like that. And did we solve all questions of the atomic world? No.
Yeah.
We
No.
cannot explain everything to the 10th or 11th digit after the comma, but we have a good grip on how that works. So we as humans or scientists or whatever, have managed to understand many things. There are many things we don't understand yet. And it's a really interesting question whether there are things we cannot possibly understand, like
Yeah.
these
Because I mean,
NP hard problems or
yeah.
whatever, whether there are
Yeah.
problems we cannot solve, whether we go into some kind of loop. But I think there are some simpler problems that still can be solved that are
Yeah. 100%.
challenging.
Yeah, 100%. I think there are many simple problems, but the consequence of solving life and consciousness could also be be quite profound, because then basically we are computers, and I am agnostic about this. I'm not saying there is something that we cannot explain, but I like to just go down that rabbit hole and say, okay, if we can build it, then we can simulate it. Therefore, we can also have a simulation of reality, which is also something that we could do. And we went down that journey with our Ex Machina book, where we try to argue and try to figure out why we are not living in a simulation. So we'll not go down that path today, but there are severe consequences. And I like to use sci-fi as science philosophy, not science fiction. And I strongly believe that mythology and folklore and enlightenment are getting a lot closer together, meaning we need more science and philosophy working together to tackle those questions, those progress topics that you just mentioned. So I'm a
Yeah,
strong.
I mean, philosophy has the freedom to think, say anything that is thinkable, and science puts you down on earth and says, okay, this is actually
Yeah,
the case in this realization of nature or so.
yeah,
But where can we break out and think further than what we think we can think? So that's a really think. Do we have free will? I
exactly.
think I do this podcast out of free will, at least I think,
But
but
your
you
neurons are
never
firing.
know.
Yeah, your neurons are firing. You are projecting it onto the world. You are thinking about your thoughts. You're not the control mechanism of your own brain to that extent. So it's very fascinating. One thing that just popped to my mind. Are you familiar with Roger Penrose and Stuart Hameroff's work on microtubuli, the orchestrated OR? The thoughts that we have neurons, and within the neurons are quantum physical phenomena. Have you dug into that?
Yeah, I think that quantum physics is, not in detail, I would say, but quantum physics, of course, is at the core of all these life functions. I mean, we know very well about photosynthesis, that it contains tunneling effect or things like that. And every molecule, the fact you sit on your chair is quantum mechanics because it's an elastic body and the quantum mechanical forces. And in deeper detail, all the molecular processes in our body are driven by quantum mechanics. And there is this randomness due to temperature because it stirs all the molecules, but there's also the quantum randomness that certain things happen now or later. I mean, there's a probability of things to happen and the probability increases. So if you look long enough on a quantum mechanical process, it always will happen. Let's say the chance to to crash with an airplane is very small, but if you live long enough and you fly every day very long, or like for thousands of years, the probability to come into a crash increases to a number very small, very, very close to 1.
Yeah.
So in quantum mechanics, if an atom makes a transition or not, if you wait long enough, eventually all the material of radiative decay will have decayed, but you don't know when it happens. So the quantum mechanical aspect is like, we don't know when something happens. It will happen eventually, but you don't know when. So this uncertainty in time plays a role on the atomistic level in our brains, and it is a chemical machine, a biochemical machine, which has the classical randomness of just temperature and molecules diffuse and stir around, and the quantum mechanical, and how that interacts and how that maybe affects us, including entanglement, which could be, at least on shorter timescales. We don't know that yet really in detail, but it's a fascinating frontier.
So it could be wet, fluffy, and at room temperature, and not and be in the
Yeah, my
brain.
God, the brain uses, what was it, 30 watt or something like that, I think, or 10 watt? Some people don't use their brain that much, so they have a lower wattage maybe, I don't know, but it's a couple of 10 watts, I think. And it does amazing traits, and it lives on the fact that it has many sub-units that interact largely. So if we take that general message to quantum computing, we need enough qubits to do something useful. We know that. And they need to be interconnected so we can really move the information from A to B. That's the key. It's an in-memory computing. The brain also has an in-memory computing. And it's not a von Neumann machine, probably. So those are really interesting questions. And I fear that I'm not young enough to live to all the explanations, but I hope we can contribute to some of this in the near future. Yeah.
That's a wonderful way to end this, Marius. It's scalability, it's interconnectivity, and I want to have you around for all these questions. And I'm very excited to see how the path for SaxonQ will go on. Where can they read up on SaxonQ and your work?
I'll just go to www.saxonq.com. We give updates. We have white paper there. We can look at some of the benefits of NV technology. You can order a quantum computer there if you want. And check us out on LinkedIn. We give you updates there. And yeah, happy to stay in contact with you on the simple and the deep questions.
Thank you so much, Marius. Thank you for coming on. It was a true pleasure, and I really enjoyed this conversation.
And it was my pleasure. Thank you.